I welcome you all for the next video on measurement of pressure measurement devices. Working principle of pressure measurement devices. It is a part of module 5 as per VTU syllabus. In the last video I had discussed about the force measuring devices and torque measuring devices. When we say power, it is the force exerted per unit area. The measurement of such a physical quantity is one of the very important aspect in mechanical engineering. There are some devices which we use it for the pressure measurement, from the simplest form to the complex engineering analysis. So let us go into the pressure measurement. Pressure, it is always represented as a force per unit area, generally exerted by a fluid on a container, and the unit for the pressure we call it as Newton per meter square or pascals. Generally, high pressures can be conveniently expressed in kilonewton per meter square, while low pressures are expressed in terms of millimeter of water or millimeter of mercury. Pressure in action of one force against another or over a surface. The pressure P of a force F distributed over an area A is defined by P is equal to F by A. Absolute pressure, it refers to the absolute value of the force per unit area exerted on the containing wall by a fluid. Atmospheric pressure, it is the pressure exerted by Earth's atmosphere and is usually measured by a barometer. At sea level, its value is very close to 1.013 into 10 raised to 5 Newton per meter square absolute, and decreases with the altitude. Gauge pressure, it represents the difference between absolute pressure and the local atmospheric pressure. Vacuum pressure, it is an absolute pressure less the atmospheric pressure, that is a negative gauge pressure. There are other means like the static and dynamic pressures. If a fluid is in equilibrium, the pressure at a point is identical in all the directions and independent of orientation. We consider or refer it as a pressure. In dynamic pressure, that is a static pressure it is. In dynamic pressure, there exists a pressure gradient within the system. To restore equilibrium, the fluid flows from region of higher pressure to the region of low pressure. Static, dynamic and impact pressures. Static pressure is the pressure of fluids or gases that are stationary or not in motion. Dynamic pressures is a pressure exerted by a fluid or a gas when it impacts on a surface or an object due to its motion or a flow. Whereas the the impact pressure is the sum of static and dynamic pressures on a surface or an object. The Pressure measuring devices can be categorized as mechanical instruments, electromechanical instruments, and electronic instruments. Mechanical instruments or devices may be of two types. The first type includes those devices in which the pressure measurement is made by balancing an unknown pressure with the known force. The second types include those employing quantitative deformation of an electric member for pressure measurements. Electromechanical instruments. This instrument employs a mechanical means for detecting the pressure and electrical means for indicating or recording the detected pressure. Electronic instruments. These instruments depends on some physical changes which can be detected and indicated or recorded electronically. So let us go to the devices. Rather than before going devices, we say some of the pressure measuring instruments, which are the elastic members. Application of pressure to certain material causes elastic deformations. The magnitude of this elastic deformation can be related to either analytically or experimentally to the applied pressure. Some of the three most important elastic members used in the measurement of pressure is Bourdon tube, diaphragms, and bellows. The working principle of Bourdon tube we can see here. The first one, uh, this is a Bourdon tube in which when a pressure is applied from this bottom end, a hydraulic pressure is created, because of which the cross section of this Bourdon tube changes. Generally, the cross section of this Bourdon tube is elliptical in manner. When a pressure is applied, this elliptical cross section changes or bulges. When the cross section changes or area increases, the end of this Bourdon tube is pulled back, because of which a displacement is created by this Bourdon tube, and when the link is connected to this Bourdon tube, that pulls the link, and this link is in turn connected to the dial indicator. So the dial indicator indicates the reading of pressure on a scale, where this is being amplified by an amplification system in between from the link to the dial indicator, so that when a pressure is created within the Bourdon tube, the Bourdon tube causes the displacement of the link with the, at the end, and that link is connected to the intermediate devices and is then finally connected to the dial indicator, dial gauge, or LVDT, so that the finally it can give the reading over a scale on the amount of pressure or the magnitude of pressure. The second one here we can see it is a diaphragm type. In this diaphragm type, when a pressure is applied, this is a flat type of diaphragms. Even the corrugated type of diaphragms are also used for the pressure measurement. In this we can see a flat type. When a pressure is being applied, in this when a flat type of diaphragms, when a pressure is being applied, it causes the deformation of this flat type or a flat elastic member, and this deformation is being censored out with the help of the gas which is present on the other side, and that is connected to the uh, other terminating devices, so that it can give the reading uh, of the pressure which is created on the other end. Third type is of bellow. Here, when a pressure is induced or when a pressure is applied, it causes the deformation of the bellows. These bellows, when it is being deformed, either it is going to expand or compress based on the type of pressure. So when it is expanding, when the bellows are expanding, the pointer over the scale rotates. The pointer over the scale rotates, indicating the amount of pressure being applied. Here it is again a second type, which is a spring type of bellow gauges, in which when a pressure is applied, these bellows either expands or compresses, or let us say first it is in a positive pressure. When it expands, because of which the pointer which is connected to the other end of the bellows or the spring that rotates and gives the reading of the magnitude of pressure. When the pressure is removed, it will come back, or the bellows will take or release the pressure and come back to its original shape or dimension, and the pointer will return to zero. This is how the pressure is being measured with the help of the elastic members. So in the pressure measuring devices, let us go to the first one. The resistance of fine wire gauges changes with the pressure according to the following linear relationship. That is, R is equal to R1 of 1 plus alpha P, where R1 indicates the resistance at 1 atmosphere in ohms, and alpha is the pressure coefficient of resistance in ohms per 100 kilonewton per meter square, where P is the pressure gauge in kilonewton per meter square. The above said resistance may be used for the measurement of pressure as high as 1 lakh atmospheric or 10,000 kilonewton per meter square. Generally, a pressure transducer based on this principle, we call it as a Bridgeman gauges. A typical gauge uses a wire of manganese, which is made up of 84% Cu, 12% Mn, and 4% Ni, wounded on a coil and enclosed in a suitable pressure container. The pressure coefficient of resistance for this material is about 2.5 into 10 raised to minus 11 per pascals. The total resistance of wire is about 100 ohms, and conventional bridge circuit may be employed for measuring the change in resistance. So the total resistance of wire is about 100 ohms, and conventional bridge circuits are employed for measuring the change in the resistance. Such gauges are subject to aging over a period of time, so that the frequent calibration is required. However, when properly calibrated, the gauges can be used for high pressure measurement with an accuracy of 0.1%. The transient response of the gauge is exceedingly good. The resistance wire itself can respond of variations in the megahertz range. Of course, the overall frequency response of the pressure measurement would be limited to much lower values because of acoustic values of the transmitting fluid. The figure indicates the Bridgeman gauges. Here you can see the pressure when it is applied from the one end. On the other side, it is the input device for this Bridgeman gauges, where the pressure is applied, and it is connected to the manganese wire, which the other end of the manganese wire is connected to the terminal, that is for the voltage source. Sorry, for the EMF source, or the output voltage source. and the whole body is connected to the one end of the EMF, that is output voltage source. The EMF across the cell body and the terminal is being compared, or the EMF generated across the cell body and the terminal is being connected to the resistance type of resistance transducers, so that we can induce the induced voltage of the change in the resistance can be connected, can be calibrated in terms of a pressure. When a pressure is applied, generally it causes the compression of the bellows, so because of which in turn the bellows apply the pressure on the manganese. This application of pressure on the manganese wire changes its resistance, and because of which the voltage across the EMF. So the change in the resistance of the manganese wire causes the change in the EMF generated across the cell body and the terminal which is connected to the wire, and that voltage change in the voltage is calibrated in terms of the pressure. By that way we can measure the pressure applied or exerted with the help of the Bridgeman gauges. Next is about the low pressure measuring equipments. Uh, in general, pressure below the atmospheric may be called as a low pressure or vacuum. Its units are in microns. Very low pressure may be defined as the pressure which are below 1 mm of mercury. Generally, McClure gauges are specially meant for measuring this kind of pressures. The working of McClure gauge is based on the Boyle's fundamental equation, which says that P1 is equal to P2 V2 by V1, or P1 V1 is equal PV is equal to constant, where P and V refers to the pressure and volume respectively. Subscripts 1 and 2 refer to the initial and final conditions in general case. Conventional McClure gauges are made up of glasses. This measures the pressures of gases by compressing a known volume of with a fixed pressure. Known volume of gases or a fluid with a fixed pressure. The new volume is then a measure of the initial absolute pressure. The McClure gauges has been used until recently for calibrating the other gauges also. It covers vacuum range between 1 to 10 raised to minus 6 star. It consists of the capillary tube C and the bulb B, and the mercury sump which is connected to the lower end of the glass tube such that it can be moved up and down, and they are at this capillary tube and bulb are then at the same pressure as that of the vacuum pressure P. The reservoir is subsequently raised until mercury fills the bulb and rises in the capillary tube to a point where level in the reference capillary R is located at the 0 point. If the volume of the capillary tube per unit length is A, then the volume of the gas in the capillary tube is given by Vc is equal to A5. Before that, the pressure to be measured is connected to the upper end of the glass part. When the mercury level in the gauge is below the cutoff EF, the unknown pressure fills the gauge, including the bulb and the capillary C. When the mercury sump is moved up, the level in the gauge rises, and when it reaches the cutoff F, or a known volume of gas at a pressure to be measured is trapped in the bulb and capillary C. Then the mercury is forced into the bulb and capillary. Assume that sump is raised to such a level that gas at the pressure to be measured, which filled the volume above the cutoff, is now compressed to the volume represented by the H, or here Y. Suppose the original volume after then mercury reaches is V0, and that is at a pressure being P1, then we can simplify it as V0 into uh, P1 is equal to AH into or AY into P1 plus H, which is equal to P1 into AH plus AH square, or V0 into P1 minus P1 into AY is equal to AY square. P1 is equal to V0 minus AY is equal to AY square. So as we assume that AY is much smaller compared to the VB or V0, then it can be neglected that P1 is equal to AY square by VB. Advantages of McClure gauges. Advantages of the McClure gauge. It is independent of the gas composition. It serves as a reference standard to calibrate other low pressure gauges. A linear relationship exists between the applied pressure and H. Further, there is no need to apply corrections to the McClure gauge readings, which makes it very versatile, and it can be that makes it as a device which can be used for calibration purpose also. Some of the limitations: the gas whose pressure to be measured should obey the Boyle's law. Moisture traps must be provided to avoid any considerable vapor into the gauge. It measures only on a sampling basis. It cannot give a continuous output. The application of McClure gauge includes it is used to measure vacuum pressure. Pirani thermal conductive gauge. Pirani thermal conductive gauge, it works on the principle that if a heated wire is placed in a closed chamber of gas, the thermal conductivity of the gas depends on the pressure. The transfer of energy from the wire to the gas is proportional to the gas pressure. If the supply of heat energy to the filament is kept constant and the pressure of gas is varied, then the temperature of the filament will alter and is therefore a method of pressure measurement. The schematic representation of the Pirani gauge, we can see it in the figure, where the bridge circuit is connected to the heating filament, which is present in a vacuum chamber or a bulb. To measure the resistance of the filament wire, the resistance bridge circuit is used. The usual method is to balance the circuit at some datum pressure. That's why generally a sealed and evacuated gauge is being used, and use of out of balance current at all pressures as a measure of relative pressures. In the figure, we can see the sealed and evacuated pressure, in which also the heated same filament is being used, which is considered as a datum. On the other side, we can see the vacuum pressure for which the pressure need to be measured, in which the similar heating element is placed. The heat loss from the filament is also a function of ambient temperature, and compensation for this effect may be achieved by connecting two gauges in series. So this similar to this, even a thermocouple vacuum gauge we can use it, which actually creates the resistance, and that resistance variation we can connect it to the output EMF source, and it is being compared with the input EMF source, and the voltage across the output EMF source can be calibrated in terms of the pressure. Let us go with in detail about the principle of this Pirani gauge. The measuring pressure gauge is first evacuated, and both measuring and seal gauges are exposed to same environmental condition. The bridge circuit is then adjusted through the resistor R2 to get a null condition. When the measuring gauge is exposed to test vacuum pressure, the deflection of bridge from the null position will be compensated for changes in environment temperature. Pirani gauges require calibration and are not suitable for the use at very low temperatures. For higher pressures, generally, the thermal conductivity changes very little with the pressure. Further, it also must be noted that heat loss from the filament is also a function of the conduction losses to the filament support and the radiation losses to the surroundings. Let us go in detail about the working principle of a Bourdon tube. Bourdon tube is one of the oldest pressure sensing element. It is the length of a metal tube of elliptical cross section and is generally shaped in a letter C. One end is left free and the other end is fixed and is open for the pressure source to be applied. A tube of elliptical cross section and has a smaller volume than a circular one of the same length and perimeter. When connected to the pressure source, it is made to accommodate more of the fluid. Resultant of all the reactions will produce maximum displacement at the free end. Within closed limits, the change in the angle subtended at the center by a tube is proportional to the change of internal pressure and within the limits of proportionality of the material. Of the material. With, I'll repeat, within the closed limits, the change in angle subtended at the center by a tube is proportional to the change of internal pressure, and obviously within the limits of proportionality of the material, the displacement of the free end is proportional to the applied pressure. The ratio between major and minor axis decides the sensitivity of the Bourdon tube. The larger is the higher in the sensitivity. Materials of the Bourdon tube is phosphorus bronze, bronze or beryllium copper. So that is about the Bourdon tube. Thank you. Uh, I think I have covered most of the things in the pressure measurement devices. Uh, I hope it is clear. If you have got any query, please post it in the please post it or send a mail. I will try to clarify those things. And further, I have used many resources in preparing this teaching material, as well as textbooks and internet sources. I acknowledge all those sources through this video, and I also thank to all those sources. I thank to all who have helped me in preparing this teaching material. Further, thank you all for watching this video. So in the next video, I will discuss on the strain gauges on strain measuring devices. Thank you all.